saw several types of knot invariance, and last time we saw this how these guys arise from quantization of algebraic curves. But in fact, as we'll see a little later, in general, one can repeat the same story for more general algebraic varieties, of course, in a very special form. Of higher dimension. So at this moment, we just saw an example of this, and we did talk sufficiently enough about quantization. So now our goal will be to focus on various types of knot invariance. And as we saw last time, there are different flavors, different species of such invariance. For example, there are various knot polynomials. Then we also touched a little bit, and we'll see maybe more of it later, knot homologies. Or, in fact, these algebraic curves themselves, and that was one of the questions from you guys last time, are also invariants of knots, and we'll talk about knot polynomials of different nature, namely the polynomials or some algebraic expressions which define, whose zero locus defines a variety, like our algebraic curve. So I guess I can also write here various varieties or spaces, or I'll just say geometry associated to a knot in some way. And this could include algebraic geometry of curves, or symplectic geometry, which is a good starting point for quantization. And in our example, these geometries were both. I mean, they were both algebraic. They equally belong to algebraic geometry and symplectic geometry. So the basic idea is very simple. For all of this invariance, the goal is as follows. If you have a knot presented to you in some form, and you have to agree, first of all, how you present a knot or a link. Knot is basically embedding of S1 in three-dimensional space. So S1 mapped into R3, so that it could be R3, S3, or potentially a more general three-manifold. It's an embedding, and by saying that it's an embedding, we mean that therefore it doesn't have self-intersection, it doesn't meet itself, it doesn't have any cusps or bad singularities. Everything is nice and smooth. So for instance, this thing where there is a singular point, or this thing is not allowed. So it's a smooth embedding. And then to every such embedding of a circle, or possibly collection of circles, so this is called a knot. Terminology is that this is definition of a knot. And likewise, link is several of these guys together. For instance, you can imagine taking the same picture as I keep drawing all the time, because that's essentially the only diagram I can draw very fast without thinking. And you can imagine linking it with something else like this. So now there are two circles embedded in the three-dimensional space, but they're linked together so they cannot disentangle. And basically, the idea is that you want to classify, distinguish all such fellows. So one way is to, well, anyways, to associate some invariant to it, and it could be a certain polynomial associated to every such diagram or every such knot, again, presented to you in whatever way. It could be a vector space or homology group H, and again, it will depend on the knot. So in general, any number of variables. So far, I'm just summarizing what's possible, and then I'll give you examples where there is one variable, two variables, and potentially more. Of course, the more variables, the better, because the stronger likely it is to be the stronger with more variables. So same, you can have some vector space associated to diagram. Here I'm going to draw a slightly different one, and so on and so forth. And finally, with geometry in the same way, you can we'll discuss examples where there is a variety, potentially with singularities, also associated to not or possibly not sitting inside a three-manifold. So you could have, again, same type of dictionary where given a knot, possibly with some decorations, additional data, you associate a geometric space. And what we saw before are two examples of this. So we saw that there are two polynomials attached to a given knot, or so I'll consider these cases in parallel. If you have a knot or a link, or more generally, in fact, a three-manifold, to every such fellow, you can associate, first of all, an algebraic curve, or this variety. So that gives you polynomial, or in general, several polynomials of one type that define this geometry and this certain moduli space that we'll discuss before. And there are also polynomials which are of a slightly different nature. They're called quantum group invariants. That whose zero locus doesn't mean anything. So zeros of these polynomials don't define anything interesting as far as we know. So they're not presenting you geometry of some moduli space, but they're a byproduct of some computation that involves quantum groups or something quantum, and that's hence the name. That's why they have this name. Now,
sorry, are the polynomials at the first case invariant?
Yes. So in both cases, all of this, right, so this is basically a list of what kind of types of knot invariants you can encounter in your career. So throughout your life, I bet you'll encounter one of these types, roughly speaking. So I'm just trying to give you a big picture. And even if you talk about polynomials, here this is subdividing the first class, if you wish. Even if you work with polynomials, they typically will come in two flavors. So there will be polynomials that define such moduli spaces, and polynomials that are byproduct of some fancy quantum computation, whatever it is. We have to understand. So therefore, my goal today is to explain what these are, in particular in our context. So for us, example of the first kind is exactly this polynomial a of xy that we started with. And in fact, it was polynomial which was a of xy, and it also depends on parameters a and t, especially in this fancy version of homework. So that's the first kind. It was obviously used for defining an algebraic curve in our case. Polynomials of this kind we also encountered a little bit. These were ZNs that we computed by recursion relation starting from the moduli space. So, and these were polynomials in, again, the several variables, for example, a, q, and t for us, okay? So they actually belong to this slightly different classes, but they both are not invariants. So in fact, I should also, perhaps if I want to make it explicit, I should also emphasize that it depends on a knot or link or three-manifold. So I can write it as an argument, as here, or sometimes it's written as a subscript, or sometimes the knot or link is omitted from the notation if it's understood that we're working with invariance of knots or three-manifolds. So then we just emphasize the variables, or sometimes people do the other way around. So my goal today is to talk about these two kinds And I'll start actually with the second one. So because this is more classical and more widely known. In fact, you also had lectures by Kashayev, and he talked a little bit about such quantum group invariance. So hopefully it will be a little bit more familiar. Now, this is basically the outline, the roadmap, how what we're going to discuss today and what we discussed last time fit together. So now, for this quantum group invariance in general, there is a polynomial for every node or link. I can call it K, and it depends on one variable Q for every choice of Lie algebra and representation. So here, G is Lie algebra, and R is a choice of its representation.
Your quantum group is quasi-classical.
Well, this is just a label. This is just a label, but of course, for every classical group, there is also quantum version, and that's so. Very often, what this invariance.
But there are some quantum groups which are not quasi-classical, so you have no underlying reality.
Yes. So.
They are polynomial.
Oh, that's a good question. I don't know. I know for some of them there are, but I don't know if for every such quantum group which doesn't have quasi-classical limit there is a polynomial. That's a good question. It has to do with one ingredient that we're going to discuss next. We need OR matrix, which satisfies Young-Baxter equation. So let's call it R. And if I denote my representation either R or corresponding vector space, we can call V, or V sub R, then this R matrix is a map from V tensor V to V tensor V, and it has to satisfy the usual Young-Baxter equation. Which graphically is typically represented as this kind of diagram. Like this. So product of three R matrices or is equal to product of three R matrices, where this is 1, 2, something like 2, 3, 1, 3, and this would be maybe 1, 3, 1, 2, 2, 3, something like that. So I'm not sure about indices, but you can restore it from this graphical notation.
Could you draw the indices of R and V if you denote this V tensor V?
Yeah, so let me come back to this and do it in a second. So in fact, I have to introduce actually what V is associated to representation. Let me come back to nodes for a second, and then I'll comment a little bit on it. So anyway, this was the answer to a question that if this quantum group has, which doesn't have quasi-classical limit, happens to have R matrix which satisfies Young-Baxter equation, then we're in business. So then we can start playing with knot invariance. Otherwise, if it doesn't, then there is no hope, basically. That's the point.
You wrote that polynomial depends on Lie algebra and its representation. Am I correct that actually you need not Lie algebra but quantum group?
Yes, you're correct, but for every Lie algebra, we know that there is universal enveloping algebra which can be deformed to a quantum group. So for each classical type, there is such a deformation, and I'm going to focus on that.
How about this deformation is not canonical?
It is canonical. It was the theorem of Cardan that Benson shows that quantum deformation is needed for all semi-simple groups.
Right, right. So then we are going to focus on this guys. Yeah. Right. So exactly, it is convenient to label this invariance, and in fact, for what I'm going to for this connection, for instance, between this type of polynomials and this type of polynomials, it is important to focus on classical. In fact, let's choose it simple and semi-simple group. Yeah. Yeah. So. This is the case which is understood best, after all, even in the territory of not invariance. So even though we want to compute quantum invariant, and it will involve this variable q, which is, as you may of course suspect, is a deformation parameter. Deformation parameter of this quantization or quantum deformation. We actually label these polynomials by classical groups, by classical choice of group Lie algebra and its representation. So knot theorists like to draw this kind of pictures by putting this representation as a decoration on the knot. So instead of writing polynomial, sometimes you may see the same, or they want to tell you that they're working with this object by drawing a knot. So I'll draw a bigger diagram of a knot like this, and they put representation R somewhere next to it, just to emphasize that they're interested in not, terminologies that they'll be working with a knot decorated or colored by representation R. So again, terminology is that this picture represents a knot, or in general a link, colored by representation R. So for instance, if you're working with SL2, and the corresponding group could be, for example, SU2 or SL2, you can choose any representation, any finite dimensional representation R of dimension n, and that would be an example which actually we secretly already encountered in the last lecture. Again, we came to it from quantization, not from knot theory, but we, again, it could be, say, n-dimensional representation of SL2, or sometimes people say SU2 if they want to emphasize the group, not the Lie algebra. But here I want to make a stress on this label n. Don't worry about whether it's a group or Lie algebra. In the case of rank 1, there is essentially only one choice. All representations are labeled by their dimension. And this index n, this so-called color, is exactly what we encountered here last time. So this n is indeed the color or choice of representation data that we need to specify in constructing such invariants. So therefore, again, claim is that for any choice of such Lie algebra and representation, there is a polynomial in one variable q that you can attach to every knot. Question, how do we construct this invariant? How is it defined? Is this clear until so far? Yeah, if there are any other questions, feel free to ask. So, as usual, it often happens that same object, same entity may have several definitions, and they may be, so it may be approached from a number of different viewpoints. For instance, if there is a really cool construction in geometry, it very likely have some meaning in algebraic geometry and also in symplectic geometry, and maybe from analysis viewpoint. So, and it actually helps sometimes to tackle it from different angles, because different viewpoints may shed new light or give complementary information or understanding of the same object. So this invariants also happen to have several different definitions which agree in the sense that when you compute this polynomial for a given knot and with the same choice of Lie algebra, you actually get the same result. this often happens if you have several schools or several countries working on the same project and they come up with different solutions. After all, they don't have to use identical tools. Generically, if we work on different problems, like on homework problems, we may come up with the same result, but solution may be slightly different. That's not very surprising. Now, one solution to this particular homework problem is that you take every such knot diagram, exactly the way I have been drawing it so far. This is called knot diagram. It's projected on a plane. And to every interesting place in the knot diagram, interesting place is exactly where two pieces of the knot, called strands, cross each other. You associate something to it. So here in this particular diagram, there are three such places. This one, and this one here. And outside of this little three-dimensional balls, I just have this piece of a knot, or corresponding strand, going on freely without doing any crossing. Nothing interesting happens. So to every such fellow, namely this three-dimensional ball where I have a crossing of a certain type, you associate an object, and this object is precisely this R matrix, which I happened to mention earlier. So in fact, I hope it's not going to be too confusing, because I also call it by letter R, but this curly R. Okay? And this R, as we already discussed, it's a map from V tensor V to V tensor V. And the reason is that if you orient the knot, which is what we're going to do most of the time, say send orientation, and it means that this continues, if it's consistent all the way, going here, here, and here, then at every piece, for example, I'll focus on this little ball, I have a map from V tensor V, and I associate V to every strand, so every, if the knot is colored by representation whose corresponding vector space or representation space is V, then what this little ball represents is basically, so I'm going to draw it here magnified a little bit. So I'm drawing three-dimensional ball, which I excavate from this diagram. Then inside the ball, I have these two strands starting somewhere and going through. So on the boundary, I have 4 points, because the strands cross this three-dimensional, the sphere. Why? Well, I can rotate it, so of course. So it's a three-dimensional picture. So no, I don't. I think, even if you rotate it, it's going to be exactly identical. So it doesn't really matter, but I think it actually is the same. So what this diagram represents, you're supposed to compute this invariant, you're supposed to translate geometric data or topology of this knottedness into algebra somehow. And the way you do it is that to every strand, here you associate this representation R. That's what it means to color the knot, or you associate the corresponding, more precisely, associate this vector space. There is interpretation of these knots in physics where this vector space V represents the Hilbert space of some particle which goes through the knot, and this particle may have several states. Just like when we discussed quantization, we saw that particle may have Hilbert space and live in different states of this vectors Hilbert space. Here is the same. Basically, you can think of this knot as a trajectory of a particle. And if this space is one-dimensional, it has only one state. If this space is n-dimensional, such as a representation of SL2, it may have n different species, flavors, and it can be any one of them, and it traverses this knot. Now, something interesting happens to this particle or object as the crossing occurs. Because here, see what happens, you have two copies of V which enter the diagram, and two copies of V, the same vector space, which go out, right? And you may have a non-trivial map from a tensor product of the first two, which don't talk to each other before they join in this crossing and go out. So that's exactly what our matrix does. It basically has a bunch of labels, ij, kl, which map you from some basis. So i's and j's label basis vectors in V tensor V here. K and L are corresponding labels for V tensor V which go out. And as a result, this R has lots of indices, but conceptually it is a map from V tensor V to itself. So is this point clear? Now, there is such an R matrix for every choice of Lie algebra representation, and this R matrix depends on Q, depends on this quantum variable Q. Now, interesting thing is that, and that's the reason I'm not going to continue with this approach any further, I just want to give you an idea that it exists, is that this object is very complicated. So in particular, this R matrix, maybe I should write it on the board here, associated to some Lie algebra representation. It doesn't depend on a knot because it encodes only local structure of such crossing. Exactly, yeah, it's not a good letter, I realize this, but unfortunately both are fairly standard, so maybe I should write, I'll try to use V whenever they come next to each other so I avoid any sort of conflict. Yes, that's absolutely right. And it depends on Q. And what I want to emphasize is that this is a very horrible object as a function of Q. So it's a power series in Q. In fact, pretty bad power series. It has lots of rational coefficients. And it's constructed in a very nice way using representation theory. So from group theory point of view, if you want to study representation theory, this is an interesting object. After all, it satisfies Young-Baxter equation and so on and so forth. But as a function, this is just generic, pretty bad function with very complicated coefficients. So the result that comes out of it is very nice and simple, and that's why I'm not going to continue with this approach further. I'm just going to say that if you want to construct this invariant, P, which is labeled by Lie algebra representation, again, it depends on knot, and as a function of Q, this is constructed in the following way. After all, we already managed to associate this R matrix to every crossing in a knot diagram. And this indices I, j, and k basically tell you how, so this is, for example, index I, j, and here on the outcome you have k and l. So then what you do, you basically continue these indices all the way, and if this is index k of the R matrix which is associated to this crossing, then if the strand continues to the other crossing, you just say that this is the same index k. You identify them. Then this is going to be L, this is also J for this R matrix, this is I, and so on and so forth. So there is an obvious rule suggested by the knot diagram how to contract the indices, and what you do, you basically take morally the trace of all these R matrices. So you write R matrix for every crossing, no, this I'll skip. This I'll skip. This is yes, it's a good subject. It's really cool, exciting, and unfortunately, it's much heavier than anything we're gonna do next. So, and I don't really need it. So, as I say, I just want you to know that this exists, and this is actually in some way rather interesting conceptual viewpoint. If you're interested, you should definitely read more. My goal here is just to let you know that such things exist and raise your appetite, give you an idea how it's constructed. That's actually the hard part. So
you gave us interpretation that we gave vector space to any piece of loop between two intersections. In the interpretation, when we work not with diagram of node, but with node itself, and have this vector space arranged.
Yes, same. In fact, it's always better to think about node itself sitting in three-dimensional space, and same data decorates the node, basically. If you want to compute some invariant, we associate vector space, which is a representation space for some Lie algebra, to actually all of the node, because it continues through. The only thing which happens is that when you pass through crossing, you have this interesting map from V tensor V2 itself. But yeah, I mean, you should think of it as a three-dimensional picture. And what we usually, I mean, we just draw it as a diagram of the node, but this is just presentation. So this is, of course, not important. In the end, we are supposed to produce an invariant which doesn't depend on presentation, which doesn't depend on projection on this two-dimensional diagram. And this is ensured by Reidemeister moves, or in this approach, it actually is a consequence of this Young-Baxter equation. That's why we need Young-Baxter. In order to prove, it will be an element in the proof that whatever we compute as a topological invariant, namely is a three-dimensional object.
No, I'm asking, is there a definition of this polynomial which do not work with diagram at all? And
yes, there is, but it will involve Chern-Simons topological quantum field theory. So I thought we did enough physics, and it would be so. Excitement after Witten's work on Chern-Simons theory was precisely that such definition was given. And until then, in fact, all the other definitions I know use diagrams one way or the other. So unfortunately, there is a choice. One has to make projection and then prove that it's independent. So it's always very nice when you can give intrinsic three-dimensional definition. Yeah, but yeah, the only one I know is based on Chern-Simons 2Q.
There is extra factor inside trace, yes? It's not usual trace, but there is some.
Well, this trace is in the following sense. So this trace is in a sense that we're supposed to, if you think about this matrices with indices I, j, k, l, and so on.
Then still there is extra factor, which is not arithmetic, but smaller one, just dimension n cross n, not n squared cross n squared.
Well. Well, yeah, right. So those facts I either want to absorb in our metrics. I'm not explaining how it's constructed anyway, so I want to give kind of basic building blocks. So that's much less important. So what you have to remember from here is that you take our metrics for every crossing. So for example, if I'm doing this particular node here, which is called trefoil node, our favorite example, there will be only 3 factors here. So then, as these components of the nodes are linked together, or this crossings, you basically contract indices in suitable way. That's what I mean by this trace. Trace means that just follow the diagram. So this quotes mean follow the diagram of the node and contract the indices, and voila, you get some result, which depends on everything that was input data. In particular, it depends on Q. But now magic happens, and magic is that, as I emphasized to you, this R matrix is a power series in Q. In fact, a pretty horrible one. It has all powers of Q till infinity. But when you take the trace, and I mean, you can write it as a rational function. It has denominators. In fact, as it was pointed out correctly, there are a couple of other minor ingredients which I'm not discussing. But when the dust settles, you get a nice polynomial in Q. In fact, exactly this kind of polynomial that we saw last time. So it was very simple polynomial with only few terms, like 2, 3 terms, and so on. So therefore, this is the reason I'm not going to continue with this approach any further, because what really happens is that you do a lot of work, and it's very complicated work. And when the dust settles, you get a very nice compact expression, which is very short and simple. So therefore, you feel that you're being cheated, that something went wrong, and there is an alternative definition which is simpler. Okay? And that's why I said from the beginning that yes, it often happens that there are alternative definitions for example, for Hovenov homology and for many other objects in mathematics, geometric or algebraic, there are often different viewpoints, and some may give you nice, cute shortcuts. So, see, I'm not going to continue this any further. I'll give you a shortcut. So something that can produce answers very, very quickly. Unfortunately, the shortcut is not going to work for any choice of representation. That's why I had to present this first, and also to intimidate you, to show that it's, it's very scary, but in reality, there is a simpler way to do things. Okay, so the alternative, so this is method number one, how to compute this invariance P for any G, any R, and as a function of Q. So for some, in fact, very few choices of the Lie algebra representation, you have an alternative which is based on scaling relations. And I don't know, did Kashaev talk to you about this? Okay.
This topic was discussed that you had mentioned earlier, but I don't know.
I see.
We have some Lie algebra and we have some representations of course.
Right. So unfortunately, this sum means very limited list. So the simplest choice is to take G, for example, to be SL2, and to take R to be the fundamental representation, two-dimensional representation of SL2. So in this case, and idea will be very similar more generally, is the following. Every time you see a crossing of this type in a diagram, you're allowed to replace it for the purpose of computing invariant. Only for the purpose of computing this, you want to define this P, G, R of Q, of course, which also depends on the knot. So for purpose of computing this invariant, you're allowed to replace it by other type of crossing. So let me move it a little to the side here. So what's the difference between these two projections from three-dimensional point of view is that you're allowed to pass one strand through the other. You're kind of allowed to snap it, make a cut, pass it through, and then glue things back. So this is, of course, not normally allowed if you're not cutting things and gluing. But the point is that for the purpose of computing this invariant, you're allowed to do this. What this means more precisely is that if you're interested in computing P invariant or your polynomial of this diagram, this means that it's piece of the knot, and there is the rest of the diagram, which I'm not drawing here, that you don't change in this process. It's a local operation. It's applied only to one crossing. Then you can replace it by P of this other type of crossing, where again, there is the rest of the diagram, which I'm not drawing, and nothing, we assume that nothing happens to it. You make only local change on one crossing. And you're allowed to do this operation, meaning that the difference between these two is either 0 or negligible. But for interesting things, it actually turns out that this is not 0. So you can do this operation at a little price. You have to pay a small price for making this change. Namely, you express it, you relate it to invariant P of another type of crossing, which is actually simplest of all. You don't have any crossing whatsoever. You just do this. Okay. Again, locally, meaning that the rest of the diagram of the node sits there and you don't do anything to it. So for instance, in the case of SL2 and two-dimensional representation, the rule is the following. You do this with some coefficients. You have coefficient q squared here. So to emphasize, let me use color chalk. Here you use q to the power minus 2, and here you use q minus q inverse. Okay. In particular, you see that if q goes to 1, which is classical limit, then this difference term, the right-hand side, vanishes. And you're literally allowed to do what we just said. You're literally allowed to pass the strings one through the other. You're literally allowed to make this transition. Again, what this diagram means is that if you see a knot, complicated knot like here, and you see some crossing, you're allowed to make a change on a blackboard and do this instead. But you have to take into account these difference terms and so on and so forth. And difference term in this case would be this kind of crossing continuum and changing the diagram. So basically what happens is that you start with this complicated diagram of a knot, and then you're allowed to make such changes to reduce it and express it in terms of simpler diagrams. So, does it make sense, or shall I illustrate it with an example? Is it? I think
we should define the period of the circle.
Exactly, yes, I'm right. We're coming to this, right. So this is one and perhaps the most interesting non-trivial piece of the scaling relation, of course. Also, you have to define what P of, suppose, yeah, you do this reduction. Then typically what happens is, starting with a complicated diagram of a knot, you reduce it to some unknotted pieces. For example, from this trefoil knot, you can get something which looks like this. After you do all these applications of moves, one of the diagrams that you'll encounter at intermediate stage will look as follows. So you completely eliminated all crossings. In fact, it's clear that when you do this exactly with this difference term, that's what you're going to get. And here you see that there are 3 unknotted circles. So you have 3 circles, which I don't remember which orientation goes, but something like this. And you have to say what it means for P of, say, unknotted circle times some other knot k. So for instance, suppose I want to call this guy k, which may be more complicated, and then it doesn't talk to unknotted circle sitting aside. Then the rule is that this is the same, in fact, for all of this invariance, as P of the unknotted circle times P of the rest of the picture, if they don't talk to each other. So the rule is that it's always multiplicative. When you have something which is not linked to your diagram, you can just cut it in the middle and then multiply the invariance. So invariants are multiplicative under this rule. In fact, more generally, if you have 2 different diagrams which are completely disjoint, by this symbol I mean that they're not only just disjoint set theoretically, but they're also not linked. There is nothing going on as far as linking number goes. Then the same is true. This is just a product of K1 and K2. And with these rules, and finally, you can see that by following these rules, you can always reduce your diagrams just to unknotted circles. You'll reduce to different linear combinations depending on which knot or link diagram you start with, but you always reduce your computation to this fellow. And therefore, the only thing which remains is to declare what this invariant is. So for us, if you're working with two-dimensional representation of SL2, very often this is taken to be so-called quantum dimension of a two-dimensional representation. Often this is written as dmq of v. And by definition, this is just a number. There is no v corresponding to it, but this number is q plus 1 over q. and it has this nice feature that in our favorite classical limit, where q goes to 1, this, of course, goes to 2, which is just actually the normal dimension of a two-dimensional representation. So this is called quantum number, if you want.
Actually, it's not clear. You gave another definition where you took trace of R matrices, and when you work with circle, you don't have any R matrices at all. You just have one.
There are this
Correct.
about trace.
Right. So right, and in a way, right. Yeah.
There is extra
Yeah.
factor.
There is right. Right. There is either small additional ingredient here, which I didn't discuss because, as I say, I'm not developing it fully.
And this
Or-
ingredient is not on the blackboard. So
Yes, this ingredient is not on the blackboard. I mean, I try to write all the big ingredients, kind of, and suppress all the small details. For example, the indices, the dependence on Q, and additional decorations, which, because it didn't matter to me, I didn't give you the definition of this R, which, again, is the most complicated part of this definition, and that would require more time. But yeah, it's not on the board here. But still, this, yeah, okay. Okay, so let's get back to here because we're supposed to take a break actually, and this is, I think, perfect time. So let's just take a break. So this finishes alternative definition of invariant for SL2 and two-dimensional representation. So after the break, we'll continue with slightly. So, okay, let's continue. What did we define? We constructed. So I told you that there is a general story, which gives polynomial that we denote by Lie algebra representation, and of course it's invariant of a knot, depends on Q. And this guy is in general called quantum group invariant or quantum polynomial. So terminology is such that this is quantum, usually you say G invariant of, and then of a knot, and so on and so forth, okay? Of the knot K. So typical case, and that's the one we're going to consider from now on, as I decided to specialize earlier, when G is SLN. So when G is SLN, then you just say that this is quantum SLN invariant. And that's actually context where you hear this notation more often, because when group is not SLN, sorry, Lie algebra is not SLN, but orthogonal, symplectic, or better yet, exceptional, these invariants have not been studied as much as they should have been. So if you look for literature on quantum SLN invariant, of what I discussed, and compare it to the amount of literature you have on orthogonal or exceptional groups, you'll find that the ratio is something like 98% to 2%. And I'm not kidding. So that's, therefore, if you're looking for a problem in this field, do anything other than SLN. And I bet almost every reasonable problem, or many of the things we're going to do today, or even what I'm presenting, has very poorly developed analog for orthogonal, symplectic, or better yet, exceptional groups. So therefore, let's just stick with SLN for most of our discussion. Of course, SL2 that I just described to you is a special case of SLN. This is n equals 2. And in the case of n equals 2, all these definitions define our fellow PSL2. In this case, representation is a fundamental two-dimensional representation. And in terms of Young diagrams, it's convenient to denote it by Young tableau, which contains single box. So this we'll use later. This invariant, which depends on knot, but most importantly depends on Q, is actually defined either this way or with R matrix, is simply the Jones polynomial. Okay. So that Jones discovered this invariant. It was the first example of a quantum group invariant of a knot, and there is a close cousin for a 3-manifold. We'll talk about it.
What is the representation?
It's a 2-dimensional representation. So this is 2-dimensional representation, but I'm slowly introducing a new notation where I'm going to denote this 2-dimensional representation either as, say, V2 to emphasize that it's a 2-dimensional vector space, or also I'll denote it by Young tableau. Young tableau that contains a single box, single diagram of a single box. So this is our first example of famous John's polynomial, which has to do with SL2. So therefore, good thing about this definition compared to the previous one is that everything is so explicit. So and then all the computations are very easy to do on what's in America we call on the back of the envelope. So meaning on a very small space, you can just on half a piece of paper.
On the margin.
Or, yes, on the margin. Well, on the margin sometimes you don't finish, and then that creates problem for further generations. But yeah, so this skein relation, so what we discussed is the so-called skein relation technique, where you just change crossings at a cost of keeping track of the powers and additional difference terms and so on, allows you to do computation very, very quickly. So for instance, example, and I want you to finish this as a homework, and again, this is really easy homework, so that's very doable, is take, for example, K to be a Hopf link. So this is not a knot, but a link given by this diagram. And then you can easily try to compute this John's polynomial. So compute P SL2 box of this guy. And in the process of computation, of course, what you have to do, you say pick orientation this way. And then if you look, say, at the top crossing over here, you see that you can change this crossing. So now this is linked in 3-dimensional space. But if you change the top crossing, which I circled over here, into the other type of crossing, as here, then you see that if I don't change the rest of the diagram, it becomes unlinked. So I'm going to traverse. So the rest of the diagram looked as follows. So I have another crossing over here. Okay. So now it's very clear that these are just two unlinked circles. You pull them apart. Each gives you a factor and so on. So keep track of these coefficients, and you'll get an answer. So of course, we also have a difference term, which corresponds to no crossing diagram. So I'm going to do the same. I'm going to draw the bottom in the same way. But now, in this part, I'm supposed to show no crossing, and that means doing this. And again, you see that this is now something very simple. We essentially ended up with a single copy of this unknotted circle, which is presented in a very funny way. But again, in 3-dimensional picture, this is clearly just unknotted circle called unknot. So this fellow is called unknot. So therefore, you have contribution of this diagram, but if you keep track of all the coefficients, powers of Q, I ask you to compute this invariant. And actually, even the some of these homeworks I'm giving you, as well as solutions, and again, the lectures I'm following are on the archive, so I'm going to give you, again, archive number. In case if you don't manage to do this homework or something is puzzling, you can look it up. In this number. And if I remember correctly, this particular homework is there, so you can have some fun. But now you can, if you feel that you're very confident, say with this case of so-called Hopf link, it's called a link, not a knot, because it has originally two pieces. you can try something else, some more complicated knot. And again, it's a lot of fun actually to do these computations because essentially I did half of this computation for you. I showed all the diagrams that contribute, and you can see that for fairly small knots, this is an interesting, fun game. Now, I have to point out that there are right, so there'll be remark. There'll be many choices and conventions. So unfortunately, everyone who wants to write a paper on this subject or any other subject introduces their own notations, their own conventions. And this subject is full of conventions which unfortunately are not very canonical and systematic. So some people, for instance, use half powers of q instead of powers of q. So sometimes you see expressions which involve half integer powers rather than integer powers. And that probably is related. The moment you see such expression, you immediately should try to double all the powers and compare it with your results if you're following these notations which are done in the other system of convention. So first of all, people use q for slightly different things which differ in a rather trivial way. Second and more important thing is that there are different normalizations of the expression. So this normalization that I showed you, where p of the unknot is given by quantum dimension, more generally, if you think about representation R of a Lie algebra G, always for the unknot you associate this sort of expression. For SL2 and two-dimensional representation, it's going to be this. I'll show you what it is for SLN in just a moment. But important thing is that it's a non-trivial expression. And this is one choice of normalization. And resulting P of any other node that you compute starting with this normalization is called unnormalized. Unnormalized quantum group invariant. Now, there is another choice that you can make. Suppose you do the computation and you compute this unnormalized fellow. Then what you can do, you can define P, say, denoted with a bar of k. This is a definition to be P of k divided by P of the unknot. Okay? This is called normalized in the literature. Also, sometimes this is called unreduced, or this version would be called reduced, because you already normalized by something else in addition. So in particular, in this normalization, if you want, by definition, p bar of this unknotted circle is going to be just 1. So sometimes if you want to communicate very quickly with your friends and ask in which conventions you're working, a quick answer could be in conventions where unknot is equal to 1. So that's one way to do it. However, I have to emphasize that going between them is not just as, well, it's not as obvious as the division by p of the unknot, especially if you have several components in the game. And you see that starting with one component, sometimes you can generate several and vice versa. So the number of link components changes. So using this normalization blindly may cause trouble. So you have to think a little bit about it if you're aiming to go back and forth between conventions. And also, when we talk about knot homologies, this is much more complicated, actually. So this is also not as obvious, and there is a preference. But anyway, I just want to pause and spend this 2 minutes to emphasize that comparing to the literature, there could be different notations, and sometimes results may look different. And typical sources is that either conventions are different or that you see 2 different versions. For instance, just to illustrate to you how it looks like, let me give the answer for this trefoil knot that we have all the time in our game. P, again, SL2, single blocks. This is the Jones polynomial of the trefoil knot. In the unnormalized version is this. It's q plus q cubed plus q to the 5 minus q to the 9. Okay. And in the normalized version, which I denote with the bar, same thing, same Jones polynomial of this trefoil knot. Well, it's basically obtained by dividing this expression by q plus q inverse. And it's interesting that you can actually do this division. So the result is q squared plus q to the 5 minus, sorry, q to the 6. Everything has to be even, minus q to the 8. Or vice versa. It's easier to see if you multiply this by q plus q inverse, you actually get this. Okay, so you see that this fellow has 3 terms, this fellow has 4 terms, and that's how the answer looks like. So in particular, it illustrates one point which I mentioned half an hour ago. It illustrates the point that the final expression is actually a polynomial, which could not have been obvious a priori. In fact, it's a polynomial with integer coefficients, which is also not obvious from any definition of such quantum group invariants. Because if you use the definition based on R matrix, even R matrix itself has matrix elements which are power series expressions in Q. So they are infinite, indefinite expansions in Q. They involve horrible rational coefficients, huge denominators. Denominators are growing very fast. However, when the dust settles and you take this trace, which I call trace in quotes, and trace the diagram and contract indices, you get very nice simple expression. This looks beautiful. This you can actually compute in 10 minutes, given the rules I told you. With R matrix, I cannot compute it in an hour. I would have to recall the definition. I would have to go to Mathematica to contract the indices. It's a horrible long expression. And yeah, after a couple of hours, I would produce the same result.
So you have no exact form of R matrix in 2x2 two-dimensional representation?
No, in two-dimensional representation, it's easier. But I mean, if you go to a...
To demonstrate horrible function.
Oh, no. Yes, unfortunately, I don't even, it's so horrible, exactly, so horrible. So this is, again, Jones polynomial, and this is why all these invariants are called polynomials, because the result is a polynomial. Very soon, it will be a rational function, not just a polynomial, but still they're much simpler than power series, of course, and then that's why they usually call polynomial expressions. Okay. Anyway, this is what we have to know. So, any questions about this part? Once we see this definition of the Jones polynomial, it's actually very easy to generalize everything to a more general story. In fact, since I use Blackboard and you guys are writing, for me it's actually very easy to make the changes. Suppose I want to take SLN. So now I'm going to be changing SL2 to SLN. Okay, I claim, so and let's take n-dimensional representation of SLN, because that's analog of two-dimensional representation of SL2. So the only thing which changes is this. So every time I see 2's, I replace them by n's. And there is a 2 here, there is a power of 2 here with a minus sign, so it becomes q to the n, q to the minus n. And I claim the result of doing this is just quantum SLN invariant. So the only thing I have to change quantum dimension. Quantum dimension is such that it has a property that in the classical limit, when q goes to 1, it becomes equal to n, and the corresponding expression. So the only rule which I really have to modify in some significant way is this one. It's an expression for, my chalk is wet for some reason, so yeah, that's the one I was using before. Okay, so it's q to the n minus q to the minus n over q minus q inverse. Okay, so if you divide this out, you see that what you get is actually, this is, the numerator is obviously divisible by denominator, because when q, I mean, they have common zeros. But then if you divide it out, you get exactly n terms, each of which is a power of q, ranging from minus n minus 1, and so on, up to n minus 1 with a positive sign. So in particular, you see that when n is equal to 2, this is indeed our familiar q plus q inverse that we had.
Term to the other? Jump in the power from one to the other. Is 1 or 2?
Oh, it's 2, yes. It's right. So you divide it out. It's easy to see that these dots contain some other terms, and in fact, it's a good exercise to do this division. You'll see that the powers jump with step 2. Yeah. Anyway, this expression is what's called quantum dimension of n-dimensional representation of SLN. It defines some invariant of your favorite knot, and this is called quantum SLN invariant. So the resulting fellow, again, SLN, and I'm going to denote it by a single Young diagram which contains single box. This is to denote fundamental or n-dimensional representation. So this guy is called quantum SLN invariant. Okay.
Hopefully it's here. Hopefully.
Right. So we're coming to it. Now, I was thinking if I should give you an example for the trefoil or continue. I think I'll continue a little bit further. Okay, so now with very little work, we did define several such invariants. So we already know Jones polynomial, we know quantum SLN invariant, and we should always think of quantum SLN invariant most of the time as associated to fundamental representation of SLN. Again, this is so-called unnormalized version. If I compute the result and divide by p of the unknot, I'll get so-called normalized version. Now, again, there is something cool about doing this on a blackboard, because I can, again, do a little magic here, erasing and so on, and produce for you yet another invariant. So continuing with these generalizations, let's introduce our third character in the game. So we're going to introduce Homolgy polynomial, and we'll do it in the following way. So here you have invariant associated to n-dimensional representation of SLN. If you look at this formula, this Kane relation, which is the key that defines such an invariant, you can ask yourself, how does it depend on n? How does it depend on the rank of the group? And that's always a good question. But if you have any problem in your hands which has anything to do with the representation theory, it's always a good question to ask. I bet you. There is always a good answer. How does the answer depend on rank? Always things behave very systematically, or there is something nice happening, or it may not be nice, then it's probably very deep. So, but it's always a good question. So here, if you ask how it depends on rank, the answer is fairly simple, because in all of these relations, n appears in very few places. And it appears always in combination q to the power n. Namely, it appears in those two factors, and it also appears in these factors. q to the n, q to the minus n, and there is no n anywhere else in this definition. So therefore, an obvious thing to do is to introduce a variable. So let's call it a, for instance, and say that a is equal to q to the n. Okay. And now all I have to do, every time I see q to the n, I replace it by variable a. After all, if n is treated as a variable, then I'm allowed to replace it by equivalently good combination, which is a. So this becomes a, this becomes a inverse, and the only two other places I have to change is this one. This is a, this is a inverse. And with this definition, what we get is something else. So of course, I have to erase this. It's no longer valid. And what we get as a result, is something that I cannot say that it's an invariant associated to SLN, because I essentially found a universal formula which works for any n, right? So therefore, I have to erase this. And if I am erasing the Lie algebra, I probably better erase a representation. But luckily, what we did, we packaged whole family of invariants labeled by the same representation. So therefore, this label, which is fundamental n-dimensional representation, or Young tableau, that's actually the reason why I decided to switch to Young tableau notations, because that doesn't change if the rank changes. So that stays the same. But as a result, we define a new invariant of a knot or link k, which is now a function of two variables. It depends on a, and it also depends on our quantum q. So what this is, this is called Humphrey PT polynomial. Well, as everything else, it's a polynomial invariant of a knot, so you don't have to say that. So that's the definition.
What is this acronym?
What? Oh, Humphrey PT. Yeah, it stands for two groups of people. So I don't remember all the names. So as usual, these are first letters of their names. In this paper, it's transmogrified. So if you look at the paper, the list of authors actually doesn't go with H, O, and so on and so forth, but it's a little rotated so that you can pronounce it, or it sounds like a word, even though, of course, it's not a word. And PT is also a paper by two other authors, which unfortunately sometimes gets omitted. That's the problem. I mean, if you're writing a paper, it's probably best to write it in a big collaboration, because what happens now that when we cite Humphrey polynomial, even I said it just now, we actually don't say PT very often. And of course, that's not very nice to these people. So, I mean, I gave you the reference, and it's in there. Yes, yes. So I don't remember all the names, unfortunately. So, yeah, so it's good to be fair and honor those who developed it or invented it. But anyway, coming back to our good old friend, so let's see. Here was an example of how John's polynomial looks like, and it has 3 terms in a normalized case and 4 terms in unnormalized case. Okay, so that much is clear. And again, I encourage you to compute it or play with this computation. Now, let's illustrate how it goes for the Humphrey polynomial. Well, quantum groups are behind the scene or under the carpet. So they enter only our matrix business. And since I didn't discuss it in detail, this is actually quantum group invariant, but we don't see quantum groups directly. what we do see is this now. Yeah, that's why skein relations are pretty cool. I mean, they allow me to not only make definitions, but also I have some spare time in this lecture to give examples, illustrate things. They're very good for quick computations. But unfortunately, they don't exist for general Lie algebra and general choice of representation. So in fact, the only examples where they work are pretty much the ones I covered here. There are a couple of more where I can define skein relations, but that's it, unfortunately. Anyway, coming back to the Homfli, so again, we can do the same, play the same game. If you have a knot diagram, you can use this relation to simplify the diagram. It will always reduce to some collection of unknotted circles. To each unknotted circle, you associate this, and then you do the computation. For instance, for the trefoil knot illustrated here, what you're going to get is the following. A square q minus 2 plus a square q square minus a to the 4. Okay. And guess what? This is a normalized version. So this is normalized Homfli polynomial. And it's really a polynomial. Well, it's a Laurent polynomial because it has also negative powers, but it's a nice polynomial. Of course, if you want to produce this unnormalized version, what you have to do, you have to take the same expression and simply multiply it by a minus a inverse, q minus q inverse, so you multiply it out, but then you get a rational function. So it's, I want to point out, of course, it's not a polynomial. What you're going to have is you'll have some numerator, and it doesn't cancel denominator. Otherwise, life would be too easy. And what you get is unnormalized version. So I should probably say Homfli PT. So what happens to me is a very typical thing when you just forget this two little p's and t's. Yeah, so still people call this Homfli polynomial or Homfli PT polynomial because it's a close cousin of polynomial invariance. And in fact, as we saw before, it does become polynomial if you specialize a equals q to the n, then you get quantum SLN invariant. And then, of course, what happens is that the moment you set a equals q to the n, which was how we arrived to this expression, you have a nice cancellation here. This fraction has nicely canceling factor, and then even this unnormalized expression becomes a Laurent polynomial. So everything is good. Now, also you see very easily that if you specialize to a equals q to the n, you do get our, again, quantum SLN invariant. For instance, in this example here, let me do it just with this reduced or normalized version. And for simplicity, I'm going to set a equals, I'll set a equals q squared. So this is supposed to give us Jones polynomial or quantum SL2 invariant. Then from this factor we have, let's see, this will be q to the 4, q minus 2, so this is therefore q squared. Again, this is a is q squared, so this is q to the 4 times q squared, this is q to the 6, and this is q to the 8th, and that's exactly the expression we had before. Okay, so this is just to illustrate that, of course, everything I said was very consistent, but this is, again, just illustrating that specialization to a equals q to the n gives us back quantum SLN invariant. And now you can also see another fellow, another remark is that in this form, these expressions here should remind you something that we already saw in the previous lecture in the expressions for Zn. For instance, expression Z1, which we computed, was essentially expression for single box. So this index 1, or little n, actually refers to number of boxes in the Young tableau. And if you look at what we had from recursion relation from this algebraic curve and so on, is indeed an expression. It was polynomial which had exactly these powers of a and q, and it had also t decoration, which made all the signs positive. But it also had 3 terms. And again, it doesn't matter what the powers are. We had exactly these 3 terms here. So that's the magic. So that's where we come to the same object from different angles. First of all, we could come to this object and its generalizations by quantizing algebraic curves. And that's what we did so far. But it also has independent definition, either based on R metrics or based on skein relations here. OK, so let's see. I have 10 more minutes, and I want to use them wisely. So let me show you a couple of more. So we'll relegate this other type of polynomial invariants, the ones which define geometry, for next time. So I don't want to rush with that. It's actually not very much work, but it's also very cute and self-contained subject. So I'll leave it for tomorrow. In fact, we'll have time for other things as well. I just don't want to rush and be quick with this. But I'll use 10 minutes for something else. We talked. I want to give you a little better idea from this perspective about knot homology. And this is actually a perfect time, and maybe some other generalizations. So as you see, all these polynomial invariants, so-called quantum group invariants, they are defined by some set of rules where you decompose your manifold or knot in a manifold in basic pieces. In the present case, these basic pieces are crossings. So Kashayev, when he gave you his lectures, was decomposing things into either crossings, which again play a role, or tetrahedra, basic simplices. So triangulation. And that's always the idea. You chop manifold or whatever object you want to study in basic ingredients and try to associate some algebraic rules to manipulating these ingredients. Now, in every definition of quantum group invariant, what happens is some sort of magic, in a sense that all the ingredients look very complicated, like R metrics. It's a power series. It has no integrality in terms of its coefficients. But the final result is very simple. It's just here on the board, or in the case of John's polynomial, we had it a moment ago. For non-trivial knot, it just has 3 terms. It looks pretty simple. And that's why you obviously expect some richer structure. So in particular, one aspect of the story is that these coefficients are always integer. And the funny thing is that even if you go to more general invariants, this PSLN, and choose any representation R of SLN, and compute the corresponding invariant, you'll produce a polynomial whose coefficients will be integer for any choice of representation. And that's quite magical, because this R matrix technique, which is the only one you have in mind for this, or Chern-Simons TQ of T, or any other technique you have, is very complicated and shows no integrality. Absolutely not. And the final result always has integer coefficients. So that's why people always thought that there should be some sort of categorification, meaning that there should be a homology theory such that this is Poincare polynomial of some homology theory. Therefore, just to make it explicit, you would expect, early characteristic, you would expect that there is another mechanism which, given a knot K, associates to it, in this case, doubly graded theory. I'll call the gradings I and J. Actually, to be consistent with notations, maybe let me put the degrees on the bottom as subscripts. And this theory, of course, also depends on G and R, which I'll put as labels here as well. And then if you sum over these degrees, sum over I and j, all integer values, with weights -1 to the I and q to the j, you're supposed to get back your quantum group invariant. So of course, existence of this homology theory would in a way explain integrality of coefficients, because they would be interpreted as dimensions of vector spaces. Oh, sorry, I have to write either dimension or rank here. So let me put rank. Otherwise, it makes no sense. I was restoring the formula from the back. That's why it got omitted. So existence of such spaces would explain integrality of the coefficients. And conversely, the fact that coefficients always come out to be integers suggests that such theories exist. So up to now, at the present day, these theories have been constructed, meaning defined mathematically, and also physically as well. There are physics conjectures like Chern-Simons 2QFT, which provide candidates for these theories for quite a few different choices. For example, one famous one where G is SL2 and representation is just fundamental, which I'll denote, or two-dimensional, which I'll denote by, again, Young tableau with a single box. This is Hoven of homology. Then there are also definitions which generalize this in various different directions. For example, there is a definition which works for same Lie algebra G, which is SL2, and representation which can be represented by Young tableau within boxes. And this is n-dimensional representation. Sorry, what? Yeah, that's the symmetric of, you can think of it, right. So this is nth symmetric representation of the fundamental. And that's the only one, I mean, that's the only family you have in case of SL2. And luckily for SL2 and any value of index n, there is such a homology theory. So now there are mathematical definitions. Actually, the problem is opposite. There are several mathematical definitions. And we don't know if they're consistent. So that's another thing. Some of them are hard to compute. So you have a definition, but you have no computation. For example, if you, with some of the definitions, you cannot even compute this invariant for this baby knot. You have a definition. You can prove that the invariant exists, but you have no idea if it's trivial or not. And then, well, you know it's non-trivial because it has this property. It categorifies some polynomial, so it cannot be totally trivial, but you don't know what the answer is. In fact, if this homology is finitely supported, for example, if it has finite support, that's not clear at all. So then, again, what else is known? It's constructed for SL2 and fundamental, constructed for more general representations of SL2. Also, if G is SLN and representation is still fundamental, so this is more like our Homfly theory, where we try to increase rank rather than dimension of representation. Again, the answer is known. And again, you have the same problem. You have several existent definitions. So mathematicians work too hard, or there are several different schools trying to solve the same problem. And unfortunately, at the present time, there is no hope that we can show that these definitions are equivalent, even though they seem to produce the same answer. So plus, this and all these invariants are hard to compute. There are various other generalizations. For general G and general R, this is still open problem, even though there are some candidates. So I should write here, to be fair, that there are many candidates. But they're all very hard to compute. So that's in a way why we're doing this, because as you saw last time, there is a way to produce the answer, which is very computable. It's very concrete. I could explain it by solving a recursion relation, how to get some of these invariants from something else. And again, that something else will be subject of from moduli spaces that we'll discuss next time. Now, let me just illustrate this in more detail for again, basic case of SL2 and fundamental representation. And you can imagine that picture is very similar for all of these generalizations. So here, say, this is just a picture of how this Hovanov homology looks like, say, for the trefoil knot. Same example that we keep all the time on the blackboard. So it's a doubly graded homology. So I'm going to draw the gradings on horizontal and vertical axis. Sorry, is there a question? So 0, 1, 2, 3. These are values of gradings of I and j. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So then the answer, so again, there is a definition of Hovanov homology, which is very similar in a way to skein relations, to this technique. So C-skein relations are defined as polynomial invariant by a set of rules which say that every time you have different types of crossing, you have to do some operation. For example, polynomials are related in a simple way by this subtraction. So what happens at the homological level is you also have some rules which define this vector spaces, or if you work over Z modules in a very similar manner. But of course, this polynomial relations, which is the key relation here, is replaced by some kind of exact sequence. So you have analogous exact sequence which relates homology groups for these building blocks, such as this guy. Then there are, and it of course repeats itself in the usual way, just like typical long exact sequence does. So you have the structure, and you have kind of exact triangle made out of this spaces. And problem is that rules that deal with this graded vector spaces are usually more complicated than rules which we saw in polynomial expression. The answer, however, is fairly simple. For example, for this trefoil knot, and in the case of Hovanov homology, what you get is that over integers, you get z factor here. So let me use color chalk for all this, guys. So you get another z here. Then in degree 5 and t degree 2, you have something, and there is term in degree 7. And finally, there is a term z in degree 9. So this is the answer for Hovanov homology of this trefoil knot, which has been our example all along in the unnormalized case. So this is unnormalized, or in homological version, it's often said unreduced case. And there, remember, John's polynomial had 4 terms. 3 of the terms had positive coefficients, and 1 term had negative coefficient. So if I want to compute this John's polynomial following this Euler characteristic rule, what's going to happen is that this I degree, which is usually called homological degree, will give me a sign. Depending on whether this grading is even or odd, I'll get a plus or minus sign. And this degree, which is usually called Q degree, will tell me the power of Q. For example, if I'm to evaluate this formula here, I'll see that this term contributes Q. This term contributes Q cubed, because, I guess I have to maybe, yeah, up to overall sign, right? So there will be a sign issue. So minus Q cubed. There is minus Q to the 5, sorry, plus. Okay, something is a little funny here. Okay, right. So maybe there is also additional. Yes, somewhere there is a sign mistake, I guess I might. But anyway, you produce a result which has plus and minus signs. In this case, it will have 4 terms. And I think, let's see, minus. I think it may be related to our previous answer by some simple change of variables or something like that. But anyway, it has 4 terms. Again, they have random signs. And sorry, I can't reproduce them right on spot. Basically, these 4 terms come from z factors in the homology. However, there is also a new phenomenon, which you see here, that there is the ingredient which you don't even see at polynomial level, namely torsion. So these homology groups often have a lot of torsion if you work over integers. And that's a new interesting feature of this homological invariance. OK, so I am officially over time.
About torsion, do you have any clause in your polynomial about this torsion?
No, no. So that's in fact, there are many ways in which these knot homologies are much stronger invariants of knots. In particular, this is one way, stronger than polynomial invariance. So you know, if they categorify something, categorify means that if you take Euler characteristic, you reproduce this invariant, you already know that they contain as much information as the corresponding quantum group invariant. But they have a chance to contain more, just like usually Euler characteristic has more information than homology. Oh, sorry, less information than homology. So same here. In particular, there is torsion. Also, there could be ranks. So it doesn't happen in this example, but what could potentially happen is that there is a term, for example, here, it can contribute to the rank. I mean, you would see it at the level of Poincare polynomial, not Euler characteristic, but there could be something in the same Q degree with even an odd T degree or homological degree. And they would obviously cancel if you take Euler characteristic, but they would not cancel if you say take Poincare polynomial. So there are several types of phenomena that can happen. And indeed, it is true that knot homologies distinguish knots way better than this quantum group invariance. For example, one funny problem with polynomial knot invariance was that if you take this whole sequence of the SL2 invariants and n-dimensional representations of SL2, this is so-called color-Jones sequence of colored because there is a non-trivial representation involved, and Jones because it's for basic SL2 case. So this is color-Jones invariant. And they don't distinguish knots called mutants. So mutation is an operation where you have a complicated knot diagram, some crazy stuff here. And then you say, let me construct another knot by surrounding some piece of it by a sphere and taking and rotating this ball. So I'm going to take this ball and reglue it back after rotation, after some transformation. So the resulting knot is going to be called mutant. So this operation is mutation. And it's a mathematical theorem that all of these invariants, you have infinite sequence of polynomial invariants, and they're very complicated. They can never distinguish this operation. But homological invariants can. And that's one good thing about knot. Even in ranks. So here, luckily, even in ranks, yes. Yeah. So they're very powerful. So that's why.
Don't your rank aren't they not expressed to polynomial?
No, it's expressed. You see, so this quantum group invariants are Euler characteristics. So if you write here T, in fact, I should do this because that's how T appears in all of this business, and it did appear for us before. If you compute graded Poincare polynomial, then you keep more information. Then, of course, you lose torsion, but you at least have a chance of detecting this phenomena, which is enough for distinguishing mutants, which is one of big problems for knot theorists. OK, I'm way over time, so I think I should stop here, and we'll do other things tomorrow.